Okay, so now let's talk about esters. Esters have a very kind of famous place in the history of organic chemistry because it was one of the first drugs that were discovered in the 1800s was aspirin. And that came from, well, it first started out by extracting this compound from willow tree bark, which was a carboxylic acid. But that, although it did reduce inflammation, it also hurt people's stomachs. So Bayer, which is one of the first drug companies, realized that it could convert the carboxylic acid into an ester, and that gives us modern day aspirin, which is much easier on our stomachs. So here we have a carboxylic acid, right? We talked about how this was a carboxylic acid group, carbonyl group with the hydroxyl group. An ester is when I have something very similar, but I've replaced the hydrogen with an alkyl group, right? So in this case, it's just a methyl group. It could be any number of carbons long. Okay, but so an ester would be when you see that almost carboxylic acid looking thing, but now we have a carbon chain on the other half, not just an OH group. So this would also be an example of an ester above. Okay, you can make esters really easily by taking a carboxylic acid and an alcohol and combining them together in the presence of acid and heat. So if we look, we have, in this case, let's just take a look real quick. We have our carboxylic acid, which has 2 carbons, and we're going to see this chunk is found in the back half here. But now we've replaced the OH group with this portion of our alcohol. So this is what makes it our ester, right? So we're combining a carboxylic acid and an alcohol in order to make an ester. And then we also have a byproduct where these two come together to form water. Okay, this is called a Fischer esterification reaction. It's a dynamic equilibrium, meaning that it's if you started out with your carboxylic acid and methanol and added heat and acid, you'd get ester. But if you started out with just an ester and water and added heat and acid, it would go the other direction. Okay, so this is one reaction where it doesn't really strongly favor the products or the reactants. You always get a mixture of both. All right, so first step is let's make sure we can spot what products we would get from a Fischer esterification reaction. So again, if we're looking at our carboxylic acid, this chunk will remain in our product. So we have that there, and it's going to combine with, it's going to combine with this portion of our alcohol. Okay, so importantly, if I'm going to like double check that I have the correct structure here, I'm going to do one of the strategies that I always, and I guess I should be good actually and add water as a product. But I'm going to do one of the strategies that I always do in organic chemistry to make sure I've got the right products and count carbons. Right, so 1, 2, 3, 4 carbons in the carboxylic acid chunk, and 1, 2, 3 carbons, 1, 2, 3 carbons in that what was formerly the alcohol chunk. Okay, same sort of idea. I should have 1, 2 carbons in my carboxylic acid portion. That's there. Great. And then lastly, this one, the alcohol chunk is a little bit more complicated, but it should, whoops, and I'm going to include that oxygen as well. Okay, and I can double check my work again by just counting. So 1, 2 for the carboxylic acid, 1, 2, and then it splits. So 1, 2, and then it splits. So I have 3, 4, 3, 4. Okay, and again, if I was being really good, I would also have water as my product. In organic chemistry, you'll see sometimes we get lazy and we only write the organic product, not the inorganic product. Okay, so now hopefully we can sort of do this without, this is what the previous slide was asking as well. Given a carboxylic acid and an alcohol, can you tell me what the ester product would be? So I'm going to do it pretty quickly. Hopefully you guys can see how this chunk right here is our alcohol. And this chunk right here is from our carboxylic acid. Okay. Again, this is I guess it was the very late 1800s. The most famous kind of like drug in the history of the world would have been aspirin, which was one of the most early discovered ones. And again, that's because the Bayer Chemical Company realized they could take this salicylic acid, which they were able to extract from willow bark. It had been used since ancient times to reduce inflammation. You can think indigenous tribes were chewing on willow bark as a way to reduce inflammation. They realized that that compound really did a good job at reducing inflammation, but again, it was hard on people's stomachs. So they could do an esterification reaction where they turned that carboxylic acid group into an ester, and that became much more gentle on people's stomachs. Wintergreen oil is actually a very kind of similar thing, where you take the salicylic acid and methyl alcohol or methanol, and you get something that's very similar in structure to aspirin, not quite the same. You can compare them to see the differences, but that's the oil of wintergreen. It has a very strong wintergreen scent. Okay. Naming esters. So let's take a look here at this compound and see if we can't figure out where this name came from. Notice that it has two portions to it. Ethyl space butanoate. So step one, note this is our new suffix, an O8, right? So butanoate is but, meaning 4 carbons long, and then it has the O8. This corresponds, the butanoate corresponds to this chunk over here. All right, I guess we can actually include the oxygen, doesn't really matter. Okay, whichever half contains the carbonyl carbon, that's going to be the parent chain, right? So if I'm just walking up to this thing, this molecule right here, and I'm going to try to name it, I'm going to figure out where that carbonyl carbon is, and that is going to be my parent chain. It doesn't matter if it's longer or shorter than the other half. Because it contains the carbonyl carbon, that's my parent chain. So in this case, the parent chain is the butanoate. And then the other half is the prefix, and we're just going to indicate how many carbons there are. So this would be ethyl, ethyl space butanoate. Okay, you can sort of think of it as the parent chain portion comes from what was formerly the carboxylic acid. This would be the parent chain, and the substituent comes from what was formerly the alcohol. So this would be, the common name here would be methyl ethanoate, right? Again, the parent chain portion or the substituent portion was from the alcohol, and the parent chain, the ethanoate, was what was formerly the carboxylic acid. Okay. Okay, so in terms of common name or Iupac names, we're not going to worry about common names. I just want you guys to focus on the Iupac names. I'm walking up to this molecule here. What am I going to do? I'm going to break it into the parent chain and the substituent. And again, the parent chain is going to be the portion that contains, I guess I can leave it purple, that contains the carbonyl carbon. That has to be a part of the parent chain. So this is my parent chain. It has 2 carbons. So it's ethanoate. That's the parent chain portion of this molecule. The substituent would be what's on the other half of that ester bond. And again, you're just going to indicate the number of carbons with the prefix we always use. This has 2 carbons, so this would be ethyl ethanoate. And very different from a lot of the functional groups that we've studied. These are 2 different words, right? We're usually slam it all together into one word. This actually has a space in between. All right. Okay. So for this one here, this is a good idea to pause and take a second and see if you can't figure this out. So again, step 1, I got to identify the parent chain, which is the longest set of carbons that contains that carbonyl carbon. So that would be this chunk here is my parent chain. I have 1, 2, 3 carbons. So my parent chain is a propanoate. Propanoate. And then I have to look on the other half of that ester bond. This is my substituent, which I'm going to just indicate the number of carbons, in this case 1. So how do we do that? Methyl. So this is methyl propanoate. Again, space between them. As always, when we have our aromatic version of whatever functional group, it gets its own special name. Okay, so in this case, this, whoops, let me be consistent with my coloring. This is my parent chain, and that has the special name benzoate. We're going to again indicate what's happening on the back half of the molecule. Here I have 2 carbons, so that's ethyl benzenoate. Okay, again, hopefully we got it down by now, but let's just make sure. What are we going to do? We're going to identify that carbonyl carbon, because the longest continuous set of carbons that contain that carbonyl carbon is my parent chain. In this case, I have 3 carbons in my parent chain, so this would be propanoate. And then again, last step is look on the other half of that ester bond and indicate how many carbons are there with the prefix. In this case, there are 2, so I would use the prefix ethyl. So ethyl propanoate. Same game. Just we'll go one more time here. So again, we have going to identify the carboxylic acid component, or I'm sorry, the carbonyl carbon component, because that's going to be my parent chain. So in this case, my parent chain has 2 carbons, so it's an ethanoate. It's the parent chain. Then I'll look on the other half of that ester bond and indicate how many carbons are there with the prefix. So this is propyl ethanoate. And notice how the substituent was actually longer, more carbons than the parent chain. That's okay, because again, the whole idea is the parent chain contains that carbonyl carbon. That's how we're identifying the parent chain for our esters. If we wanted to go the reverse direction and draw esters corresponding to these names, we're going to just kind of go backwards here. So my parent chain is the pentanoate. So how many carbons? Should be 5. That 5 contains that carbonyl carbon. And then on the other half of that ester bond is the propyl. So that means I would have 1, 2, 3 carbons over here. Okay. 1, 2, 3, 4, 5 on the parent chain portion and 3 on the substituent portion. I guess this would be kind of a good time to like, well, what if I had, let's say like a substituent here, a methyl group over here? You're going to include that on the parent chain portion of the name. So you're going to start numbering from the carbonyl carbon, 1, 2, 3, 4, 5. Notice I don't have to specify, this is not 1 pentanoate, it's just pentanoate because I'm going to just assume that carbonyl carbon is carbon 1. But so this would be propyl, same back half of the ester portion. Now on the parent chain portion of the name, I'm going to include the 4-methyl pentanoate. Right, so notice that this 4-methyl gets included on that parent chain portion because it is indeed located on that portion within the molecule. Okay, and ethyl propanoate, I'm going to make sure to have 3 carbons and start that ester group and then finish it off with the 2 from the ethyl. Okay, likewise, what if there was a substituent, but this time it was on this portion of the molecule, right? This is my parent chain because it contains the carbonyl carbon, so that's still a propanoate. But now I'm going to include my substituent. I'm going to start numbering from that carbon that's connected to that oxygen. That gets to be carbon 1. So this is carbon 2. So this would be 1-methyl ethyl, all one word. 1-methyl ethyl space propanoate. So notice that where you include that substituent depends on where it is on your ester. If it's on the, the other half of the ester bond that doesn't include the carbonyl carbon, then it goes on that front word. If it's on the back half, contained on that parent chain, it goes on the second word. Okay.